Hi everyone, welcome to my new video in my Mathematics Essential series. Okay, this one will be on the proper definitions of some hopefully familiar trigonometric functions. I assume a certain level of mathematics in this series. Definitions of trigonometric functions. Okay, cosine, sine, and tangent. Okay, or cos, sine, and tan for short. And if I'm assuming that you are familiar with them in some sense, why would I make a video on them? Well, you may not be familiar with their proper definitions. Okay, you probably got introduced to them as defined in terms of angles, relationships between angles and side lengths of a right angle triangle. So this will be a video on the proper definition. And I'm referring to, by proper definition, the unit circle definition of cos, sine, and tan, respectively. So when you first got introduced to these trigonometric functions, it was probably like this. Okay, you were told to consider a right angle triangle, okay, and some angle theta, right? And from picking an angle theta in the right angle triangle, it then makes sense to talk about a side that's adjacent to our angle theta and a side that's opposite our angle theta, as well as a hypotenuse, which is always going to be the same side regardless of where we took our angle. Okay, so understand that the opposite and the adjacent sides would swap if we were talking about an angle up here instead. Let's call it phi. Okay, so the opposite side and the adjacent side would swap in relation to phi. Okay, but the hypotenuse, that side is always going to be the same side, which is the one that's opposite the right angle. Okay, so this is assumed knowledge. All right, and then you are taught that sine of our angle theta is equal to the opposite side over the length of the hypotenuse, so the length of the opposite side over the hypotenuse, and that the cosine of theta is equal to the adjacent side, the length of the adjacent side over the length of the hypotenuse, and that tan, the tangent of theta, is equal to the opposite side over the adjacent side. Okay, now I just want you to notice here that if we took sine of theta divided by the cosine of theta, well, that would equal, well, sine of theta is opposite over hypotenuse, so opposite over hypotenuse, divided by the cosine of theta. Well, cosine of theta is adjacent over hypotenuse. Okay, and dividing by a fraction is the same as multiplying by a reciprocal, so we can rewrite this as opposite over hypotenuse times hypotenuse over adjacent. Okay, the hypotenuse will cancel, the two h variables will cancel, and we'll be left with opposite over adjacent. But what do you know? That's just equal to tan of theta. Okay, so already from these definitions, we can see that tan of theta just equals sine of theta over cosine of theta, which is just going to boil down to the length of the opposite side over the length of the adjacent side when we are talking about right angle triangles. Okay, so that's important to note. But anyways, this is probably how you are first introduced to these trigonometric functions. And turns out that we need a way of making sense of sine, cosine, and tan when we are doing mathematics beyond the realm of right angle triangles. So I won't go into them, but there are many contexts in which it makes sense to talk about these trigonometric functions when whatever we are interested in doesn't really have any direct relation to right angle triangles. You can always sort of interpret things in terms of right angle triangles, but we need to move beyond these definitions. So historically, these were taken to be the definitions, and then we extended the definitions in order to allow for more applications of these, both in just pure mathematics and applied mathematics. And many scientific models in physics, for instance, would not be possible if we just stuck with these definitions. So we need to move beyond them. So historically, we extended the definitions of these three functions, and then these three are taken to follow from that more, we took the new definition to be more fundamental, and these three follow from that more fundamental definition. So if we are going to extend the definition or come up with a new definition for them, what we're going to have to do is at least two things, okay? We need to preserve these three, okay? So our new definition must respect these three relationships in right angle triangles. So we need to preserve them, and it needs to generate meaning without reference to right angled triangles. Okay? And I'm sure you're familiar with just doing trigonometry on triangles that are not right angled triangles and still needing to make use of these trigonometric functions. Okay, so that's an obvious application of these functions that move beyond the realm of right angled triangles. So let's cut the chit chat and get to this fundamental definition, which is called the unit circle definition of right angled triangles. So even though the subject matter of trigonometry is triangles and their geometric relationships between angles and side lengths, this definition actually starts with a circle, and specifically the unit circle. And it's called the unit circle because it has a radius of 1. Okay, so radius being half the diameter. All right, if I just drew a line from the center of the circle to any point on the circumference, right, and I call that the radius, which I denote with a lowercase r, okay, its length, okay, would just be 1. Okay, that's what it means to be a unit circle. So I can take any point. I could take a point out here, and if I drew a line from the center to that point, its length would be 1 as well, because all of the points on the circumference of a circle are equidistant. Okay, another way to say this is that the radius of a circle is constant. I could swing this point around anywhere on the circle, and the length of the radius wouldn't change. The radius remains constant. Okay, so now usually when we are talking about unit circles, we are thinking about them on a Cartesian plane. So I'm going to superimpose this circle onto our Cartesian plane. In other words, actually that's, in other words, an XY plane. That wasn't very well centered. I don't want it to be perfect, but I want it to look good, just like when I dress up. Okay, so there's a horizontal x-axis, close enough. And here would be our vertical y-axis. Okay, I'm happy. All right, so let's label our axes, and this is x, that's the horizontal axis that holds all our x values, and this is y, the vertical axis that holds all of our y values. Okay, this here in the center, that's the origin. Okay, and I'm just, rather than calling it the point O, I'll call it the point A so we don't confuse it with 0. Okay, it's going to have coordinates with x and y components, but because it's the origin, we know that x and y are going to equal 0. Okay, now what I'm going to do is I'm going to take some random point out here on the circumference, and then I'm going to call that point B, okay? And B is a point, so it must have some coordinates. We don't know what those coordinates are, so we're just going to call them x and y, okay? So all we're saying there is that B must have some x component and y component that make up its coordinates, all right? And now what I'm going to do is draw a line between the origin, which is point A, and the green point, which is point B. Okay, so here's my line. And as soon as I draw that line, you can see that what I've done is define some angle measured anti-clockwise from the positive x-axis to the line that connects points A and B. All right, and convention is to measure angles anti-clockwise from the positive x-axis. That squiggly arrow irks me. That's better. No more irk. Anyways, now we have everything we need to define those trigonometric functions in terms of the unit circle. So let's get to it. By definition, the cosine of theta, okay, is just going to equal x. And similarly, definitionally, the sine of theta is going to equal y, so long as this circle is a unit circle. Okay? Now, what about tan? Well, tan of theta is just going to equal the quotient sine theta divided by the cosine of theta. Okay? And you can see that that respects that fact that we uncovered about tan of theta up here with those right angle triangle centric definitions of sine, cos, and tan. All right, but we know that the sine of theta is just y and the cosine of theta is just x, so this really comes down to saying y over x. All right, but now we can also express the coordinates of b another way. Okay, we can say that the coordinates of b are equal to the cosine of theta as the x component and the sine of theta as the y component. Now, remember, definitions are conventions. Okay, so definitions are always choices, but they are smart choices. Okay, and in a later video, I am going, or actually in the very next video, I'm going to explain. Well, you see, actually, we've made no reference to right angle triangles. Okay, so I'm going to explain how this unit circle definition of these three trigonometric values preserves our right angle triangle more familiar ways of thinking about sine, cosine, and tangent. Okay, it should be clear already how we have defined these three trigonometric functions without reference to right angle triangles. Okay, we have not referred to any right angle triangles here. Of course, you can imagine there being a right angle triangle. Okay, so this would define a right angle triangle, and hint, hint, that's going to be how we achieve this. Okay, but right now I'm explaining this. We haven't made any reference to right angle triangles in our definitions, which means we can take this definition beyond applications of just right angle triangles. All we have referred to is a unit circle on a Cartesian plane, and a Cartesian plane has an origin, right, full of points, and we just picked one of the points to be on the circumference of the circle and noted that that would define an angle between the line that connects those 2 points and the x-axis, right? And from that, we just defined the cosine of theta to be x, all right? And we defined the sine of theta to be y, and the tangent of theta to be sine of theta over cosine of theta, which just boils down to saying y over x. So we have achieved a definition that does not make reference to right angle triangles, which means we can take its application beyond, or their applications beyond right angle triangles. Okay, so this is explained in this video, and in the next video, this will be explained. Okay, if you enjoyed this video, please give it a like. Feel free to share it with your friends, and if you would like a notification when I upload a new video, subscribe to my channel. Until next time, bye for now.